continuing with Michael Spivak's Calculus, Chapter 2. And as I mentioned already in one of the descriptions, but I may have realized that just going through all of the problems and just reading the book is perhaps questionable in regards to copyrights and such. So I will change the type of content a bit, of course still continuing with this book, but instead of going through all the problems, perhaps just solving them, I'll rather focus on a lesser amount of problems and try to add more of my own insight and ideas to it. And that way I think I can add enough value on top of the book that it should be okay for me to cover it. I mean, I of course understand that a person who makes a book wishes to sell it, so if I just show you all of the pages of the book, then I basically just decrease their sales. So I realized that, and I will change it up a bit. And today we are focusing on these kinds of sums, because in the last lesson we learned about induction. So let's first try to do some induction proofs. Prove the following: 1 squared until n squared sum is equal to this. So, chapter 2, 1I. So, first, if n equal to 1, then, well, left hand side is equal to 1, and right hand side is equal to 1 times 2 times 3 over 6 equal to 1. So we just put this formula into use here. And thus this formula is at least true for n equal to 1. And then what is the next step in induction? Induction. We assume true for some k. So we assume 1 plus 1 squared plus k squared is equal to k times k plus 1 times 2k plus 1 over 6. And then we try to prove that this, by doing this assumption, we have to show that it's also true for k plus 1. So let's, and well, how we can do that is by somehow manipulating this expression to instead match for n equal to k plus 1. And if that expression is kind of analogous to this one, you know what I mean, then we have proven it. So on the left hand side we would also want k plus 1 squared. So let's add k plus 1 squared to both sides. So the left hand side is like this. And then the right hand side is this expression. plus 1 squared. And then we just need to somehow combine these two expressions. That's a plus. And we'll notice a common factor here, k plus 1. So let's take the common factor out. And also, like, we can do this like 2 over 2. So we have the corresponding denominators. So it's this thing over 2. So we take k plus 1 as the common factor. Make square brackets. In here we have, from this expression we have k times 2k plus 1. And in here we have 2 times k plus 1 left over. Oh, why is this over 2? It should be over 6. I'm sorry. So it's 6 over 6. This is 6 and this is 6. Yes. Sorry. So then it's equal to k plus 1 times well, it's probably best to just factor everything out. So we have then 2k squared plus k plus 6k plus 6 over 6. And so 2k squared plus 7k plus 6. And well, this happens to factor nicely. Sorry. So it's k plus 1. And then we need to somehow factorize this. And well, it just happens to be k plus 2 times 2k. So it's 2k squared plus k plus 1. Does this work? Wait. So it's 2k squared plus 3k plus 4k plus 6. Yeah. Over 6. And then if we, let's make it more explicit. So this is k plus 1. This is k plus 1 plus 1. And then the last one is 2 times k plus 1 plus 1 over 6. And well, this is again just 1 squared plus k plus 1 squared. So we show, by assuming that this formula is true for k, we were able to show that that implies that it's also true for k plus 1, because we showed that 1 squared until k plus 1 squared is equal to this, which matches the formula. And since we all showed that it's true for n equal to 1, then because it's true for n equal to 1, it's true for 2, and because of that it's true for 3, and so on. Thus we exhaust all natural numbers, so this formula is true for all natural numbers. 1 squared until n squared is equal to n times n plus 1 times 2n plus 1 over 6. Then let's try doing equals the sum of natural numbers squared. So 1ii. Let's again do the case n equal to 1 first. If n is equal to 1, then left hand side is equal to 1 cubed equal to 1, and right hand side is equal to 1 squared equal to 1. So that is trivially true. Then assume again for k 1 cubed until k cubed is equal to 1 okay, squared. And then again just add k plus 1 cubed this time to both sides, and we get 1 cubed plus k plus 1 cubed equal to 1 plus k squared plus k plus 1 cubed. Then let's try to make this. We have to make this expression look like 1 plus k plus 1 squared. And well, we know a formula for this. It's k times k plus 1 over 2, and now it's squared. And this is let's just keep it k plus 1 cubed. Let's square this out, so it's k squared times k plus 1 squared over 4 plus 4 over 4 times k plus 1 cubed. And now let's, similar to the last one, take the k plus 1 factor out. Actually k plus 1 squared factor out. So k plus 1 squared times k squared plus 4 times k plus 1 over 4. So we got the k squared from here and the 4k plus 1 from here. And let's multiply this out, so it's k plus 1 squared times k squared plus 4k plus 4 over 4. And we can factor this into, that's actually just k plus 2 squared, so this is k plus 1 squared times k plus 2 squared over 4, which is equal to k plus 1 times k plus 2 over 2 squared, which is equal to 1 plus until k plus 1 squared. Because, well, this is just the sum of natural numbers until k plus 1 inside the square. And thus we have shown that if we assume this formula true for k, we also find that it's true for k plus 1. And since our base case n equal to 1 was true, we again are able to exhaust all natural numbers. I think I went through this quite quickly, but I hope you were able to follow. Induction proofs are easy in the sense that if you know the formula to be true, you can kind of maybe it's stupid, but you don't have to be so careful, because because you know that if you end up with the wrong result, you've done a mistake. And well, but they are also quite straightforward, especially this sum proofs, I think. But then the next problem, number 2, asks us to find the formula. Find the formula for sum 2i minus 1. So the sum of odd numbers until some n. So 2i, we want to find 1 plus 3 plus 5 plus 2n minus 1. And I'll first show you maybe the algebraic way of doing it, and then I'll show you some geometric interpretations of this. Actually, I'll show you first the geometric interpretation. So, well, first of all, if you just write sum, well, the first sum is of course 1, the second sum is 4, the next sum is 9, because 1 plus 3 plus 5 is 9, plus 7 is 16, plus 9 is 25. Do you notice a pattern? The quick-minded of you might have realized that these are all squares, and in fact this sum is equal to just, the formula is just n squared. But how do we show this? Well, one idea, I'll show it on. You can do like a geometric interpretation of this. First we have just 1, so we do 1 block. Then we add 3. So we add 3 blocks like this. And you see it's a square. Then we add 9 blocks. 1, 2, 3, 4, 9. Oh no, we had 5 blocks. 1, 2, 3, 4, 5. Again a square. Then we had 7 blocks. 9 blocks, etc. So you see that these odd numbers create, the sums of odd numbers are squares, because we always just add this kind of L shape here. I'm sure many people have already studied this a lot, but I was proud of myself for coming up with this myself. And you can, and I guess the reasoning for this is that you always just, we start with 1, so it's a square, and then you always add 2 squares more than in the previous step, which then creates this nice pattern. But how would one do this more like symbolically or with algebra? Well, Spivak gives is what do these expressions have to do with 1 plus 2 plus 3 plus 2n? Well, 1 plus 2 plus 2n minus 1 plus 3 plus 5 plus 2n minus 1 is equal to the sum of the even numbers. I'm not actually sure this is what Spivak wants, but this is how I would do it. And then of course for this there's also a geometric interpretation. Turns out the sum of even numbers is equal to n squared plus n squared plus n. Until if you do it until 2n. So the sum of even numbers until 2n is n squared plus n. And then the geometric kind of idea behind this is that, okay, first we have just a 2, so we have 1 plus n squared plus n, so 1 plus 1. Then we add 4, so we add so now we have 2 blocks, so we have a square plus we have 2 plus 2 squared, and then we add 6, it goes here, and then we always cut like this out. This is 3 squared and plus 3, and then we add 8 here, so we always have thickness of 2, and then we cut this out, so then we have 4 squared plus 4, and you can continue like this, always cutting one side out to get a square and then adding that in there. So that's kind of the geometric interpretation as to why n squared plus the sum of even numbers is n squared plus n. But how do we just calculate the sum of the even numbers, maybe more symbolically? Let me check my notes. Well, I would split this into 2 cases. First, consider that n is even. Then we have a case like 2 plus 4 plus 6 plus 8, because So yeah, like in this case, n is kind of equal to n is even, so we have and n is equal to 4 here, because we have 4 numbers. And then we can kind of, well, let's not put any equal to anything specific, but just sum plus sum 2n. And if n is even, we have even amount of these, which means and then we can, and it actually makes it easier if we add a 0 here, which gives us an odd number of numbers. Then we pair these numbers up like this. 2n goes with 0, 2n minus 2 goes with 2, and so on. And thus we get n over 2 times 2n. But the middle number, which is n, does not pair with anything, so we just add plus n. And so this is n squared plus n. So we kind of pair these numbers up. One number doesn't get a pair, and so we get this. So if n is even, then this at least formula is true. Okay, then if n is odd, then we have like again 2 plus 4 plus 6 plus some 2n. No, but that also, the same idea works for n is odd because 2n is still even. Yeah, sorry, okay. So we don't even have to assume that n is even. So that's how you can find the formula for the sum of even natural numbers. And, well, but we were asked to find the sum of odd natural numbers. And, well, we found that, well, we considered the sum of natural numbers until 2n minus the sum of even numbers, and found that to be equal to n squared plus n. And well, by doing some manipulation, we find that 1 plus 3 plus 2n minus 1 is equal to the sum of all natural numbers until 2n minus n squared plus n. And well, this is equal to 2n times 2n plus 1 over 2 minus 2 times n squared plus n over 2 is equal to well, 2n squared plus 2n minus 2n squared, no, 4n squared plus 2n minus 2n over 2 is equal to 2n squared over 2 is equal to n squared. Sorry, I again did it quite quickly, but you can pause here to confirm my workings. But again, the basic idea is just some basic algebraic manipulation, and we find that the sum of odd numbers is equal to n squared, which I think is quite nice. let's still do 2i. The sum of odd squares. For this I didn't come up yet with any geometric interpretation. I mean, how you could try to do it is like we have at the first one layer, which is 1, and then we add a layer 9, and then like this, and then you can somehow calculate the volume of this, of stacking these layers, but I couldn't find a nice way to do it. So let's do it the algebraic way. So 1 squared plus 3 squared plus until 2n minus 1 squared. And well, the key here is that 2i minus 1 squared is equal to 4i squared minus 4i plus 1, and thus sum from I equal to 1 to n of 2i minus 1 squared is equal to 4 times the sum of I equal to 1 until n I squared minus 4 times the sum from I equal to 1 until n I plus n, and that's equal to 4 times, well, we have the sum of squares here, so it's I times I plus 1 times 2i plus 1 over 6 minus, well, that's just the sum of this is just the sum of natural numbers, so I times I plus 1 over 2 plus n, and then we just try to simplify. So well, let's first try to combine these two expressions. We get let's take the I times I plus 1 common factor out. Then we have 4 times 2i plus 1 minus 12 over 6, and then plus n on the side here. And let's open the thing inside the brackets, so let's keep the common factor I times I plus 1. And then it's 8i minus 8, right? Yeah. Over 6 plus n. So it's equal to 8 times I plus 1 times I minus 1 over. Oh, I've been working with I, but it should be n, right? Yeah, it should be n. So let's put n here. Yeah, I make so many silly mistakes, but I hope I usually realize them at the end. let's try to combine the n here also. So it's so let's take the common factor n, such then n times 8m plus 1 times n minus 1 plus 6 over 6 is equal to n times 8n squared. And then, well, this is just then minus 2 over 6 is equal to 1 over 3 n times 4n. I'll write it here. 1 over 3 times n times 4n squared minus 1. Because we divided by 2 both the numerator and the denominator. And thus the sum of odd squares is equal to this. We find a formula like this for the sum of odd squares. If you know some kind of visualization for this sum, please let me know. I do love some geometric intuition. But so, I actually wanted to cover more problems in this video, but I think it's gonna be for next time, because now I need to go. I hope you enjoyed this video and maybe learned something new and got relaxed. Remember that the main thing in life is to know your mind. And so, train your mind and also train your body. And have a good evening, or morning, or day, or night. Thank you for watching. It's been Blue